Okay. Uh, Hello, everyone. Today we will continue with state space representation, and this is going to be our fourth video on this topic, and we will try to go over some properties of state space representations. Okay, so let's put again our general title here. State space representation. This is our part 4. And so what we have done up to this point is we defined what state space representation looks like. We have seen some examples on how we can derive a state space representation for a given system by defining certain states. We have seen how we can obtain the state space representation for, actually, we have first seen how we can obtain the transfer function for a given state space representation. We have also seen that there are multiple ways we can obtain a state space representation for a given transfer function model. Since there are infinitely many such state space representation, we have seen some canonical forms. Okay. Now we will focus today on some properties of state space representations. Okay, and in particular, we will talk about two important properties, okay? Namely, we will talk about controllability and observability, okay? Observability. Now, if you remember in state space canonical forms, canonical by definition means something of importance, exemplary. Okay, so canonical forms means they are special state space representations with special state definitions. Today we will show that these representations will also correspond with these particular properties of system representations. Okay, let's take a look at, first of all, let's take a look at controllability. Okay, so what does it mean that the state space representation is controllable? Okay, now loosely speaking, what controllability means is that it's related with whether we can control the system or not. That means it is related with the ability of being able to take the system from any given initial state to a well-defined final state given enough time and suitable inputs. Okay, so let me first kind of summarize that. So this is not a formal definition. This just explains what we mean by controllability. So loosely speaking, controllability is related with being able to bring the system state representation state from any given initial state to any desirable final state given enough time that what we mean is finite time, okay, finite time, and appropriate inputs. Okay, so what we mean by this is that if a system is not controllable, okay, if a system is not controllable, that means one may not be able to bring some states to the desired final values, whatever the input and even your given infinite amount of time. Okay, one may not be able to bring some states. It doesn't mean that you cannot bring all of the states. Some you may be able to bring some states to their desired values, but some other states you will not be able to do that. Okay, some states to the desired values, whatever the inputs, and given any amount of finite time. Okay, so let's kind of sit back and think about what this means. It means that this is related with the effect of the input on the states. So how we can affect the states by using the inputs, but also it also relates with the interrelation of the states with each other. Okay, because you can affect some of the states by the inputs, and those states might affect other states, so eventually you might be able to access all the states by using the inputs. So that's what we mean that the system is controllable. Okay, so it's related with both the effect of the inputs on the states as well as the effect of the states among themselves. And not surprisingly, this means that controllability will be related with A and B matrices. That means A, which defines how the states are related with each other, and B, which defines how the input is actually affecting the state space. Okay, so this is related with the effect of the inputs S within parentheses on the states, and the self-interaction between the states. Naturally, determining controllability involves matrices A and B. Okay, so let's make a formal definition now, mathematical definition of controllability. Okay, so definition of controllability. First of all, the definition starts with a given initial state. So we start by defining that a state x0 is said to be controllable if and only if, which we often shortcut with IFF, there exists some input u of t that transfers x0, that transfers this initial state x0 to the origin in finite time. So we first define that an initial state x0 is controllable if it can be brought to the origin by a suitable input in finite time. Okay? If all states are controllable, by the above definition, then the representation representation is also an important keyword here, is said to be controllable. Or the pair AB is controllable. Okay, so it is important to note here that we are not talking about a property of a system. We are talking about a property of a particular state space representation. Okay, remember that for a given transfer function, we can have infinitely many different state space representations, and this definition means that some of those may be controllable, some of them might not be controllable. Okay, so some questions to think about. In fact, I will provide the answers for questions. Sorry, So one question is that what is the relationship between the controllable canonical form, and controllability? And the answer to that is that in fact a system representation, a state space representation is in controllable canonical form is always controllable. Okay, a state space representation in controllable canonical form is always controllable. Okay, and later on we will in fact prove this. Another question that I partially answered is controllability a property of a system? And the answer to that is no, because this property is not associated with a system, but it's associated with a particular state space representation. Okay, so controllability is not a property of a system, but associated with the chosen state space representation. Okay. So now comes the question of how can we determine controllability? And the following theorem states how we can do that. We will not prove this theorem, but maybe later on I will show you an example from discrete time which shows why this theorem is valid, although the proof will be restricted to discrete time systems, and you don't exactly know a lot about discrete time systems at this point. Okay, so theorem again about controllability. So the theorem says the pair AB, which involves the matrices A and B. Remember that we have a system given by x dot equals AX plus BU. X, obviously everything is matrices and vectors here. C is equal to CX. You see that we are not in controllability, we are not interested in the C matrix, but we are only interested in A and B matrices. So the pair AB, okay, or the representation, let's call this a representation star. A representation star is completely controllable if and only if the rank of matrix Q, known as the controllability matrix, which is composed by augmenting these matrix products A to the n minus 1b, is equal to n. Or equivalently, by the way, n here is the order of the system, right? The number of states in the system. So we all equivalently, what we are saying is that the determinant of Q, which can also be indicated like this, is actually different from 0. Okay, so Q being full rank, Q is an n by n matrix, right? This becomes an n by n matrix. So this matrix being full rank means that its determinant is not equal to 0. Okay, so that is a test for controllability, is known as the controllability theorem. Now I will go over some examples, intuitive examples, and then later on we will use this theorem to actually show you how the theorem can be used to check for controllability. Okay, so let's take a look at an example. Let's say that we are given a second order system. So we have x1 dot, x2 dot, is given by alpha 0, 0 beta times x1, x2 plus 1, 0 times u. So this is a single input system, so there is only a scalar u. So let's expand this and we are talking about whether this system is controllable or not. So the question is, given any initial state, x0, can I bring this state to the origin given finite amount of time? So let's take a look at the explicit state equations. So I have x1 dot equals alpha times x1 plus u, and x2 dot is equal to beta times x2 and 0 times u. Okay, so you see that this at least says that x2 of t in fact behaves so-called autonomously. So the input does not have any effect on what happens with x2. Okay, so it's going to start from its initial value and it will behave according to its dynamics determined by beta. Okay, now let us check some initial states. Okay, let's check some initial states. So let's say that x0 is equal to 1 and 0. Okay, so the initial state for x1 is equal to 1. The initial state for x2 is 0. So we can see that x2 will actually start from 0 and will stay at 0. Why? Because whatever the value of beta, nothing's going to happen with x2 because the initial the initial value becomes 0. So x2 will stay at 0, and x1 actually we have input affecting x1, so we can actually find an input that brings x1 to 0. Okay, so with an appropriate u of t, we can bring x1 to 0, and x2 already stays at 0. So that means for this initial state, we can say that we can bring this initial state to 0 given appropriate inputs. But remember, controllability is related with being able to bring all initial states to the origin. Okay, so we need to try another initial state. Okay, so let's say that x0 bar is another initial state, and this time it is, sorry about that, it is 0 and 1. So this time the first state is at 0. So if we select u to be null, equals to 0 for all time, x1 will stay at 0. But what about x2? Okay, now with x2, in fact, you cannot bring x2. For example, if beta is larger than 1, from the initial state x2 at 0, x2 will just grow to infinity. Okay, so you cannot bring x2 of t to 0 by choosing an input u of t, because u does not have any effect. Okay, because u does not have any effect on x2, and x1 and x2 are not connected to each other. So that means your effect on x1 will not affect x2 in some way. Okay. Now, so let's check. So Q, the controllability matrix, is given by B and AB for a second order system. So B, as you can see from the system, is 1 and 0. So 1, 0. And A times B, okay? So let's also calculate A times B. A, remember, is alpha 0, 0, beta. And B is 0 and 1. So if you calculate that, you will have alpha times 0, 0 times 1. This is 0. And this is 0 times 0, beta times 1. Sorry, is that correct? Sorry about that. My B is not correct. So let's erase this B. So my B was 1 and 0. So in this case, alpha times 1 plus 0 times 0. So you have alpha over here and 0 times 1, beta times 0, 0 over here. So you will have alpha and 0 in the second column. Okay. So because we have an all 0 row here, okay, in fact, determinant of Q is equal to 0. So this is a singular matrix. Okay. Not completely controllable. Okay. All right. Now you might be saying, okay, this example was kind of obvious if I had connection. If U was actually affecting both states, I would have had a controllable system. Okay, so let me show you an example that kind of explore an interesting behavior. So let's say that A is equal to the same matrix, but this time let's say that B matrix is equal to 1 and 1. So that means U actually has an effect on both states. Okay. So now both states are connected to the input. Is the representation completely controllable? Okay. So now let's first consider first alpha is equal to beta. Okay, so alpha is equal to beta, so both states have the same behavior. Okay. Let's kind of write down again the state equations. So I will have x1 dot equals alpha times x1 plus u, and x2 dot is equal to beta times x1 plus u. And given alpha equals beta, I have x1 dot equals alpha times x1 plus u. x2 dot is equal to alpha times x1. Sorry about that. What I'm saying, this has to be x2, and this also needs to be x2. So x2 and alpha x2 plus u. Okay. Now remember, in order for the system to be completely controllable, you should be able to bring in the state to the origin given any arbitrary initial state. So let's consider a state. Let's call this x0. And let's say that this state is 10 and minus 10. Okay. Now, this is an interesting initial state because if you think about it, x1's initial state is 10. So if you think about the first state equation, in order to bring Okay, so consider this first equation where alpha is in both equations. In order to bring x1 to the origin, you should actually make u negative, so that you actually have somehow you should choose u in such a way that x1 dot is negative, so that it decreases towards the origin. But at the same time, x0, x2 initial state is minus 10. So for that choice of u, that state will actually keep decreasing as well, because they have the same dynamics. Okay, so if you try to bring x1 to 0, you will make x2 go away from 0. And if you want to make x2 go to 0, you will make x1 going away from 0. So that's kind of a dilemma between the two of the states. Okay, so you see that in this example, with this particular initial state, we cannot actually transfer both states, both plus 1, plus 10, and minus 10 to actually let's say to 0 at the same time, to 0 at the same time, meaning that by the same input. Whatever that input is, whatever that input is. Okay, so this system does not seem to be completely controllable, at least for alpha equals beta. Let us check the controllability matrix. And I'm going to check this for the general case. So check Q. Q is equal to BAB again. So that's going to be, in this case, 1 alpha and 1 beta. Okay? So you see that determinant of Q actually is equal to beta minus alpha. Okay, so this is equal to 0 if and only if alpha is equal to beta. So that means for alpha equals beta, system representation is not completely controllable. But for alpha different from beta, system representation is completely controllable. Okay, oops. All right, now let's also talk about what about a system representation given in controllable canonical form? We claimed that this is always completely controllable. So let us check. Okay, so example, let's first start with a transfer function, put it into its controllable canonical form. So g of s, let's say it's given by s plus 1 and s cubed plus 0.1 s squared plus s plus 10. Its controllable canonical form, AC, is given by 0, 1, 0, 0, 0, 1, and then the coefficients from the characteristic equation. And also for the B matrix, let's call it BC, and that is given by the coefficients of the numerator, so 0, 0, 1. Okay, so the coefficient of S square is sorry about that. In the case of the controllable canonical form, actually the B matrix is already given by 0, 0, 1, and C matrix is actually given by the coefficient of this coefficient 1 plus the coefficient of S and the coefficient of S square, which is 0 in this case. Okay, so what about the controllability matrix Q? It is given by B, AB, A square B. Okay, now let's calculate A square. Okay, if you calculate A square, in fact AC square, okay, is the product of A with itself, and please check this by calculating the matrix multiplication, but you will get this particular matrix, okay, is minus 10, minus 1, minus 0.1, and 1, minus 9.9, and minus 0.99 will be the coefficients. Okay, so again Q will be, please again check this, is that first the B vector, right, by itself 0, 0, 1, then the A matrix multiplied by the B vector, so that's going to turn out to be 0, 1, minus 0.1, and finally A square B from actually you can calculate this from this A square that I've given to you, so 1 minus 0.1 and minus 0.99. Okay, so that's our Q matrix. Now, how to calculate the determinant of Q? Now, this is a 3 by 3 matrix, and please review, review calculating the determinant of 2 by 2 and 3 by 3 matrices. In fact, in this case, I will calculate this by choosing, I will put plus, minus, plus here, and I will hide these two row and columns, and we know that this determinant will be plus 1 times the determinant of this matrix here, and that's going to be plus 1 times 0 times minus 0.1 minus 1 times 1. Okay, so that's going to be equal to minus 1, and that will be different from 0. Okay, so this is completely controllable. In fact, if I'm not mistaken, the controllability matrix, the determinant of the controllability matrix of a controllable canonical form representation always turns out to be minus 1. Okay. Okay. I think Let's see whether we should finish for now. Okay, let me put an optional example before finishing. This is not going to be included in our reviews, okay, or in our exams. Example, which is an optional example. It's kind of the proof of the controllability theorem. For discrete time systems. So in fact, if you in your next year, if you take the discrete time control lectures, like for example 402, you will see this in detail, but this is still very intuitive. Okay, so what is a discrete time system? Okay, so a discrete time system is where you have a time index rather than a continuous time. So what you have is that the state at time k plus 1 is equal to a times the state at time k plus b times the input at time k, k being the discrete time index. In fact, many properties are more intuitive for discrete time systems because you can iteratively explore what happens with the state. Okay? So what is our question is that we try to obtain u at time k such that any given x0 in basically n time steps, a finite number of steps, actually is taken to the zero state. Okay? So can we solve this problem? Can we find is a number of inputs for n time steps such that we can take any initial state to the zero state? Okay, so let's try to see what happens with this. Okay, so for example, at time k is equal to 0, okay, so we have x0, our initial state. Okay, so we can calculate x1 as a times x0 plus b times u0. And the question is, can we make this equal to the zero state? Okay. Now that does not seem to be easy. Okay, because at this point, at least, we don't know how to pick u0 to be able to do that. Let's consider k is equal to 1. In this case, the state x at time 2 becomes a times x1 plus b times u1. So you have another input now. You have u0 and u1, two different values of input. Now let's expand this because we know what x1 is. x1 is a times x0 plus b times u0 and plus b times u1. Okay, so what does that mean? That means I have a squared times x0 plus a times b times u0 plus b times u1. Okay, now I can write this in so the question is whether you can make this equal to 0. Okay, the zero vector. So this question, the same question, can be written as a matrix equation because you can take this to the other side of the equation, a squared x0. So minus a squared x0 is it or can it be made equal to, now I will put this as a matrix, B AB times U1 U0. Okay, so the question is, can you make this equality hold? Can you find can I find U1 U0 such that equality holds? Okay, now at this point, you know, BAB is not a square matrix yet, because okay, for an nth order system. So okay, so let's say that this is our nth order system, meaning that the state is of dimension n. So at this point, BAB is not a square matrix yet. Let me continue with this line of thinking. For k is equal to 2, okay, so I continue with this. So I have minus a to the power 3 x0. Can it be made equal to b AB a square b times U2, U1, and U0. Now, if you continue this up to k is equal to n minus 1, in this case, you will have minus a to the power n x0. Can it be made equal to b AB a to the power n minus 1b times un minus 1, un minus 2 up to u0. Now at this point, okay, this is basically an n by n matrix. So it's a square matrix. Okay, let's call this qn by n. So at k is equal to n minus 1, q n by n is a square matrix. Now let's see what happens if this matrix is non-singular. If qn by n is non-singular, qn by n can be inverted. That means qn by n to the power minus 1 can be found. Okay, so what does that mean is that I can actually multiply both sides of this equation by the inverse of qn by n. Okay, so that's going to mean that on one side you will just have the input sequence, un by minus 1, n minus 2 up to u0. The matrix multiplied by its inverse will be the identity matrix, okay, which is going to just go away from this equation. And then on the right or on the left hand side, you will have q to the power minus 1, a to the power n times x0. And that is the solution of the equality, which is the input sequence that brings x0 to the origin. Okay, so that means if this matrix, which you see is equal to the controllability matrix, okay, controllability matrix. In fact, if it's non-singular, then we have a unique solution for the input. Okay, we can just invert this matrix and multiply with minus a to the power n x0, and that's going to give us the input sequence. Okay, that's going to be our input sequence. So that is an example how we can actually prove the controllability theorem, but this proof is not for continuous time, it is for a discrete time example, which is outside of our scope right now. So this just for those of you who are curious, and those of you who might be in the 4th year, might be taking our discrete time control courses, is actually a nice example that is a proof of the controllability theorem. So I'm going to break here and we will continue with our next video the next time.